Alright, Lecture 8. We're going to go over Section 19.2, Acid-Base Titration, and talk about titration curves. So let's get started. So what is an acid-base titration curve? Well, it's the determined concentration of acid or base solutions. So how do we find these concentrations? Well, we use a technique called titration, where we have a burette. So in this burette, we have a known concentration of a strong acid or base. So we know a whole lot about this. We know the concentration of this amount. What we don't know is how many milliliters we're going to use inside of our flask. So here's our flask. So inside of our flask is a known volume of solution you want to measure the concentration of. So we don't know the concentration, but we definitely know the volume of this solution. Now I'm going to talk about two terms that you need to know, and Alright, so the two terms I need you to know is equivalence point and end point. So what is an equivalence point? An equivalence point occurs when the number of moles of added hydroxide equals the number of moles of hydronium originally present. When you have a strong acid and a strong base, this always happens at pH equals 7. Now when you have a weak acid and a strong base, or a weak base with a strong acid, your equivalence point will not be at pH equals 7. Again, pH equals 7 for the equivalence point is only for a strong acid with a strong base. Now what is an endpoint? Well, this occurs when the indicator changes color. So in practice, the visible endpoint signals the invisible equivalence point. So if you remember in Chem 200 when you did titration and you used phenolphthalein, well, that was our indicator telling us we were at the endpoint, which showed us that slight pink color, which informed us we are at the invisible equivalence point. Alright, so now let's move on. Alright. So I'm going to be titrating a strong acid with a strong base. So inside of my burette is my strong acid, and inside of my flask is my strong base, sodium hydroxide. Now the first thing I want to do is find the equivalence point. This is where you always want to start when you're looking at titration. So the first thing I'm going to do is I'm going to find the volume you need to reach the equivalence point. To do that, I need to find the balanced equation. So I'm going to take my hydrochloric acid, which is an aqueous solution, plus sodium hydroxide, an aqueous solution, and when I combine it, I'm going to form water plus sodium chloride in aqueous solution. Now once I've done that, I'm able to go from the volume of my base to the moles of my base. From the moles of my base, I can go from the moles to acids, and then from the moles of my acid to the volume of my acid of how much I'm going to use to get to that equivalence point. So here we go. So I have 100 milliliters. I'm going to convert it into liters. Then I'm going to take my molarity and convert it into moles. Then I'm going to do the mole ratio, which happens to be a 1:1. And now that I'm in moles of my acid, I'm going to put it into my liters using the molarity to get 50.0 milliliters of HCl. So I need 50.0 milliliters of hydrochloric acid to get to my equivalence point. So let's go stepwise. So if I add 0 milliliters of HCl, what is going on? Well, the first thing I want to know is what's in the flask. Well, I know I'm just going to have sodium hydroxide, aqueous. So that means if it's aqueous, it's in water. Alright, so because I only have sodium hydroxide, I know that sodium hydroxide is a strong base, So that means it's equal to the hydroxide concentration, which gives me 0.050 molar. So what is the pH? Well, if I have hydroxide, I can go to pOH. So to get to pOH, it's equal to the negative log of the hydroxide, and I'm going to get 1.30, and my pH is equal to 14 minus pOH, which gives me 12.70. Now, you can go from the hydroxide to hydronium and then find the pH. It's up to you. It doesn't matter which way you go. It's all the same. So when I add 0 milliliters of HCl, my pH is at 12.70. So this is where I'm starting. So my pH is at 12.70, which makes sense because it's a strong base. It's very close to 14. Now, let's see what happens when we add 10 milliliters of hydrochloric acid. What is my pH? Well, the first thing I need to think about is, well, what's in the flask? Well, I just added some hydrochloric acid, but because it gets all absorbed by the sodium hydroxide, I still have sodium hydroxide, some water that gets formed, remember your balance equation, as well as some sodium chloride aqueous solution. Again, that hydrochloric acid gets completely absorbed by the sodium hydroxide to form NaCl. So now what we're going to do is we're going to figure out how much hydroxide is there. So we're going to look at the sodium hydroxide and how much is left over. So we're going to look at the moles of NaOH that is left all over the total volume. Now, to find the moles of NaOH that is left, we need to look at how many moles of HCl we initially start with all over the total volume minus the moles of NaOH that we added. So let's go through that. So we started with 100 milliliters of NaOH. We have 0.05 molar of NaOH. We're going to minus that from 10 milliliters because that's how much we added of hydrochloric acid. We're going to multiply that by its concentration of 0.100 molar. And we're going to divide that by the total volume. So we have 100 milliliters plus 10 milliliters to give us 110 milliliters. Now, don't forget to convert your milliliters to liters because it's a molarity problem. I'm just going to keep into milliliters just to not confuse you, but please remember you need to convert your milliliters to liters, so don't forget. Alright, so this will give me 3.6 times 10 to the minus 3 molarity of NaOH, which also equals the hydroxide. Remember, you have a strong base, so we can say it is hydroxide, which is going to give us a 1-to-1. Now, because I am looking for the pH, I need to convert this into pOH to find pH. So here we go. So the pOH, again, is equal to the negative log of our hydroxide, and that's going to give me 2.44. And then I'm going to find the pH by taking 14 minus pOH, which will give me 12.56. So it looks like we are decreasing from 12.7 to 12.56 when we're adding a strong acid. So let's move on. So now what happens if we add 50 milliliters of HCl? Well, we know at 50 milliliters, when we add that of HCl, we are actually at our equilibrium point. So when we're at our equilibrium point for a strong acid and a strong base, we know that our pH is equal to 7. So again, when we are at the equilibrium point for a strong acid and a strong base, our pH will equal 7. So we don't even need to do a calculation. We only need to know that the pH is equal to 7. So what happens when we pass the equivalence point and we add 60 milliliters of HCl? Well, what do we have in the flask? Well, the first thing we have is more HCl, some sodium chloride, some water, but we no longer have any more of the hydroxide. Why? Because it's all been used up to form sodium chloride when we have too much of hydrochloric acid. So because we have too much hydrochloric acid, we are now looking at acid, hydrochloric acid. So hydronium, which represents our strong acid, is going to equal to our strong acid of hydrochloric acid, but the extra amount. So let's figure this out. So if we're looking for hydronium, which we know is equal to HCl extra amount, we are going to look at the moles of HCl extra that was added all over the total volume. Alright, so how many moles of HCl extra do we have? Well, what was the extra volume? Well, we added 10 milliliters more past the equivalence point. So we had 10 milliliters. We're going to multiply it by its molarity to give us the moles all over the total volume. So we have 60 milliliters plus 100 milliliters that we started with the hydroxide to give us 160 milliliters. This will equal to 6.3 times 10 to the minus third molar, which is equal to our hydronium. Alright, so since we have hydronium, we can now find the pH. So pH is equal to the negative log of hydronium, which will give us a pH of 2.20, which makes sense because now we're at a strong acid and we need to be less than 7 for our pH. So when we draw the titration curve of our strong base, which is in our flask, with a strong acid, we're going to see this divot. So we know our equilibrium is at pH of 7. So we're just going to go do. And we know our volume for that was at 50.0 milliliters. Now up here is our strong base, and below here is our strong acid. Now one thing I forgot to mention was when we are at pH of 7, when we are at a strong acid, strong base at equilibrium, we know that we have neutral ions. So in this case, it would just be the sodium ion and the chlorine ion. And this is, again, for strong acids, strong bases at equilibrium. So this is what a titration curve looks for when you have a strong base in your flask going to a strong acid. Now let's take a look at another example. Alright, so let's look at a titration of a weak base to strong acid. So we have 100 milliliters of 0.05 molar NH3. We know that NH3, or ammonia, is a weak base. Then we have in our burette 0.100 molar of HCl, which we know is a strong acid. So the first thing we're going to do is we're going to find the volume you need to reach the equilibrium point. So to do that, we need to create a balanced equation. So here we go. We have ammonia aqueous plus hydrochloric acid aqueous. We're going to form ammonium, NH4 plus aqueous, plus a chlorine ion, aqueous. Now we're going to find the volume we need to reach that equilibrium point, and to do that we're going to take the volume of ammonia and we're going to multiply it by the molarity of ammonia to give us the moles of ammonia. And then we're going to do a ratio to get us to the moles of hydrochloric acid. And then we're going to divide the molarity of hydrochloric acid to get us the volume we need to reach equilibrium. So here we go. Alright, so we have 100 milliliters. We're going to convert that into liters. So milli, 1 liter. Then we're going to take that molarity, multiply it. Then we know it's a 1-to-1 ratio, just looking at the balanced equation. So we are now at HCl. And then we're going to divide by the molarity of hydrochloric acid to give us the volume. And the volume we're going to get is 50.0 milliliters. So I converted this from liters. Okay, so this is the amount we need to reach equilibrium point. So what happens if we're at 0 milliliters of hydrochloric acid? Let's see what happens. So the first thing we need to ask ourselves is, if we don't have any hydrochloric acid inside of the flask, well, what is in the flask? Well, what we know is we have ammonia, which is an aqueous solution, so that means it's in water. And because we know ammonia is a weak base, we're going to need to find the KB. Now to find the KB, we are going to look in Appendix C. It so happens that ammonia is in Appendix C under the KBs. For some appendix, sometimes ammonium is under the Ka, so you might have to use that. So why do we need to use Kb? Well, we know when we're dealing with a weak base, we use this equation Kb of x squared all over the initial of our molarity. So in this case, it's going to be the ammonia. And we're just going to plug in what we know. So we found the Kb to be 1.8 times 10 to the minus 5. We know that x is going to represent our hydroxide, and we know the initial of our ammonia, which is 0.050 molar. So then we just find x, which we know again is equal to our hydroxide, and we get 9.5 times 10 to the minus 4. Now, because again we're looking for pH, we are going to find the pOH, so we're going to use the negative log of the hydroxide, and we're going to get pOH is equal to 3.02. And now we're going to find the pH. So pH is equal to 14 minus pOH, which will give us 10.977. So when we round, we actually get 11.00. And because we know that ammonia is a weak base, 11.00 makes sense. So let's move on. Alright, so this time we're going to add in 10 milliliters of hydrochloric acid. So what is now in this flask? Well, we still have ammonia. Now because we are adding the hydrochloric acid, we are forming, should be an and, ammonium plus some chlorine ions. Again, the hydrochloric acid is being used up by the ammonia to form ammonium. Now if we look here, we notice something interesting. We have our weak acid and our weak base. So anytime we have what we call the buffer zone or buffer solutions, we can use the Henderson-Hasselbalch equation, which we are going to do for this part of the equation. Alright, so the first piece of the puzzle I need to find is the pKa. Well, I know that the Kb of ammonia is equal to 1.8 times 10 to the minus 5. I also know I can use the equation Kw is equal to Ka times Kb, and if I'm looking for Ka, it's going to give me Kw all over Kb. So when I plug this in, I get 5.6 times 10 to the minus 10. Now I need to find the pKa, so pKa is equal to the negative log, and I get 9.25. Now, how do I figure out the ratio? Alright, so the first thing I need to do is I'm going to draw a little box. And I know for equilibrium I need to be at 50 milliliters. Well, if I added only 10 milliliters of the acid, I have 40 milliliters of the base left. So that means of the base, I have 4/5 of the base all over 1/5 of the acid, which gives me 4. So let's plug this in to the Henderson-Hasselbalch equation. So the pH is equal to 9.25 plus the log of 4, and I get a pH of 9.85. So as we can see, I'm going from 11 pH to 9.85 when I'm adding in that strong acid, which makes sense. Let's move on. Now what happens if we add 25 milliliters of hydrochloric acid? So again, we are not at equilibrium, so we are actually right before it. Remember, equilibrium again is at 50.0 milliliters. So again, we're going to be using the Henderson-Hasselbalch equation because in our flask, we're going to still have ammonia, we're going to have ammonium, we're going to have some chlorine ions. So we're going to use the same problem and the same format. So again, I'm just going to draw out how much it is to get to the equilibrium point, which is at 50 milliliters. Well, if I'm at 25 milliliters, I'm actually halfway to the equilibrium point. So that means my base and my acid is going to be the same, which means it's going to equal to 1. And when we plug this into the log of 1 is 0, that means our pKa and our pH are going to equal one another. So our pKa, again, is 9.25, that we found from our Ka. So for this part of the equation, our pH will equal our pKa. So now when we add 50 milliliters of hydrochloric acid, we are at the equivalence point. And unlike a strong acid with a strong base, our pH is not going to equal to 7. Alright, so what is in our flask? Well, we used up the hydrochloric acid, and we are now just with the ions. So we have ammonium, and we have chlorine ions, and that's it. So because the chlorine ion is neutral because it comes from a strong acid, and we know that ammonium is a weak acid, we're going to be focusing on the weak acid. So from previous, we know that the weak acid, the Ka dissociation, is equal to 5.6 times 10 to the minus 10 that we found in problem 3. Alright, now we're going to try to find how much of molarity we have of ammonium. So the equation we're going to use is the moles of ammonium all over the total volume, which really means the moles of ammonia all over the total volume. Alright, so what we're going to do is we're going to take our molarity, 0.1050 molarity of ammonia, multiply it by how many milliliters we used all over our total volume. So we had 100 milliliters of ammonia, and we added 50 milliliters of hydrochloric acid, and we're going to get 3.33 times 10 to the minus 2 molarity. So now that we have ammonium, we're going to find the hydronium. So how do we do this? We use the dissociation constant. So we know the Ka dissociation is NH3 times hydronium all over ammonium equals the Ka. Now we've done this in chapter 18 where we get x squared all over the ammonium initial, and we don't need to minus x because we know this is a weak acid. So now we're just going to plug in. So we're going to look for x because x also represents hydronium, and what we get is 4.3 times 10 to the minus 6. So now that we have hydronium, we can find the pH. So the pH is equal to the negative log of hydronium, and we get 5.36. This is the pH at equilibrium when we have a weak base go to a strong acid. Alright, so what happens when we add 60 milliliters of hydrochloric acid? So this means we are 10 milliliters beyond our equilibrium point. So just like we did for the strong acid, strong base, we're going to find the excess of a hydrochloric acid. So that gives us hydronium is equal to hydrochloric acid excess, which is the moles of HCl excess is equal to the total volume. Let's figure this out. So we get 6.25 times 10 to the minus 3. Now let's find the pH. So pH is equal to the negative log of hydronium, which gives me 2.20. Now let's take a look at a graph. So here is the titration curve. We have our weak base here, goes into a buffer zone, then we get our equivalence point, which is less than 7, and then our strong acid.